my name is Phineas. I've been working with Q probably for like 6 years-ish now. I started my journey with Q at Citibank, and then I was at UBS. And then now I'm at Jump, so kind of getting them to use Q a little bit as well. This is, for other reasons, I'm not going to talk anything about what I actually do at Jump, but this is not dissimilar from things that we do in terms of like manipulating matrices, using kernels and things like that. So the topic of this talk is liquid rescaling, which is, I feel like I'm going to walk here. Liquid rescaling, which is a talk on basically how you can resize images dynamically. So you are on a page and you're a narrow screen and you want to shrink your image, or you're on maybe the opposite, on a super wide screen and you want to expand your image. So this talk is going to kind of cover how you can do that dynamically without losing content, without squishing your images, without making it look funny. So, okay. So first, let's just load an image. So, oh, that's not what I want. Okay, I'm just going to do this. So if you want to load an image, I'm using PyKX, so you just open your image, and then you use NumPy to go and grab the image. You have your shape, and the shape of the image is the width, the height, the width, and then there's 3 channels. So here we can display the image. So here's this is Bruegel's The Harvesters. It's a relatively famous image of a bunch of, it's like one of the first images of peasants, basically. Before that, only nobility got to be painted. And so you can see it's a rather wide image. So we're going to try to figure out how we can kind of manipulate it and shrink it down. So the first step is, let's just convert it to what's called the level. So if you take the 3 channels, so there's a red channel, there's a green channel, and a blue channel, and you don't weight them equally. It's kind of like humans perceive colors in different ways. So what you kind of want to do is you scale, certain colors are perceived more dramatically than others. So greens are perceived more dramatically, so you kind of weight those more. And that gives you the level of the image. So if you think about it, that's kind of familiar to you as the grayscale version. So this is the grayscale version of the original image. And you can see that all we have to do is just weight it by those fractions, and that gives you the grayscale. Now we're going to try to detect the edges. So just going back, you kind of can see that there's a tree, there are different pieces, there are people there. So we don't want to remove the things that are very obvious. We kind of want to remove the background. So trying to do edge detection. So first step is we're going to use convolutions. Convolution sounds fancy, but it's basically you're going to look at every pixel and then the neighbors around it, and then do some calculation and try to figure out what's going on at that pixel. So whenever we see so the first thing we need, just as a primitive thing, is we need a shape. So basically you can think of it as the shape is going to tell you what this matrix looks like. And in Q, it's kind of a nice elegant way of getting the shape, is you just apply first over a scan. So you can see this backslash, so you apply first to the multidimensional array. You keep grabbing the first element. Eventually you're going to grab just one element, and you're going to be done. And when you've gotten to that first element, you can just count along the way how many elements there were along each dimension. So as you grabbed it, you kind of peel the onion, and every time you can kind of ask how many there were. So that gives us our shape primitive. So this is what a convolution looks like. This is sort of I think the best animation of what it looks like. You can kind of see that there's 9 neighbors, and for every 9 neighbors, we're grabbing and dropping 1 point out, and that gives you that the value at that point. So you're just kind of looking at the 8 neighbors around it plus the point in the middle. So fundamentally, when we're looking at neighbors, the first function that comes to mind is xprev. So xprev kind of gives you the neighbors next to the pixel, whatever you're looking at. So if we just grab an array that's 1 till 8, so 1, 2, 3, 4, 5, 6, 7, and then we just say, give me the first previous, the 0th previous, and the negative 1 previous. So basically, give me the next. So that will return to you 1 row for each of those. So we'll give you the first previous, which is 0 through 7, then the original array, which is just 1 through 8, and then the next one, which will be 2 through 8, and then a 0 filled at the end because we don't know what the next item is. So that's kind of the basics of xprev. So now we can kind of extend this to 2 dimensions. So now we can take the same 1, 2, 3, 4, 5, 6, 7, 8 array vector and reshape into 2 by 4. So now we can ask and we call this M. So this is just our matrix. This is just sort of give an intuition of how we can kind of manipulate this matrix. So we can take one prev of each row. So what that'll do is that'll shift all the rows. So 1, 2, 3, 4 becomes 0, 1, 2, 3. 5, 6, 7, 8 becomes 0, 5, 6, 7. So far, and then whenever we see that there's a null, we can just fill it in with 0 because we just assume that there's nothing going on outside the image. So that's just what I'm going to be doing from now on. Whenever you see a null, like whenever we're falling off the vector, we just replace it with zeros. So now we can imagine doing this for all three shifts. So we can shift it one forward, one backward, and one to the side. So we'll get basically 3 matrices and then the 2 by 4. So 3 of one shifted, one back, one forward, and then one just staying the same. So kind of just give you like a visual of what that looks like. You can think of them as like little matrices on top of each other, stacked on top of each other. So the first one is one shifted, the second one is the original, and then the last one is just shifted forward. What's really neat about this is that you can just then do this again and get the full 9 neighbors. So here's how we can think of that. So first, let's just shift the first matrix, one previous, and then what you'll see is that there's a little bit of a bug, which is that when you shift one row up, the queue doesn't really know how many elements to put there, so it just gives you an empty list. And that's kind of what we're going to fix. So to do that, we're just going to take 4 of the element that we are grabbing, and that will fix it, that'll fill it in with zeros. Because you can think of it as like, you have a nice matrix, and the row above it is always going to be full of zeros. And the row below is also going to be full of zeros. So that's like a nice little thing that you can just do and just plug it in. So then we can look at all 3 shifts of the first matrix. So that gives us the first shifted up, the first shifted like that, the second one is just going to be the same, and then the last one's going to be shifted down, so again, it's going to be covered as zeros. So this is just the first one slice of this 3 by 3 thing. And this is the full thing. So you can think of it, the middle element is sort of the identity, that's the original matrix, and then everything else is just going to be these shifts, these like little windows on top of this matrix. So that gives you that. And this is that's all the code that does that. It's just really the shifter. So shifter basically just says shift everything by 1, 0, and -1, and then apply shifter twice, and that's that 2's doing. Shape 2, shifter just says apply that thing twice and grab it from the matrix. And that gives you a 3 by 3 by 2 by 4, which is what we wanted because we wanted 9 elements for every single element in every single pixel. So that's kind of, and like why are we doing all this thing? So just as a side note, you can kind of fix the xprev behavior when you shift down the rows, because all you need to do is just say, I know what the first row has, so let me just multiply by that by the null, and I'll get back the original one. That sort of. So we can then flatten the whole thing out, and then we have this. So if you look, you can see there's the original matrix, and then down every column is like all of its neighbors. And you can see, for example, for the first element, and I've highlighted them, the neighbors of the first element are 2, 6, and 5. And you'll see them 1, 2, 6, and 5, and everything else is zeros. And then every single column kind of aligns with that. So 2 will have the neighbors 1, 2, 3, 4, 5, 6, 7. So you can see it's basically, its neighbors are 1, 5, 6, 7, and 3, and those are going to be in the second column, and so on. So as you go down, you see all the neighbors that it has. So this is the full function to just do that convolution, and you can see that it's just basically it's just that one line to pull out a convolution for any matrix. And then next thing we need is a kernel or a filter. So this is going to allow us to actually detect the edges, because okay, we've seen the pixels around, but how do you know that you're at an edge? So think about it like this: if let's say I want to detect a vertical edge, then the way there's a vertical edge is that you're going from, as you move from right to left, something's changing. If nothing changes, it's not an edge; it's just the same. So that's why what we can see is you have 1 and -1. So basically, it's saying take my left neighbor and take my right neighbor. Sorry, take my left neighbor, take my right neighbor, and subtract them, and see if there's a difference. If there's no difference, then obviously there's nothing going on in the vertical space. If there is a difference, then I'm going to put something out there. So that's going to be my kernel. And then if you flip that, you can do the same thing horizontally, and you get a horizontal edge. So here's what that looks like. So you can see all the vertical edges. And pay attention, the tree has a nice vertical edge, but you can see there's a field, and the field has a big flat thing, which is just a black canvas, and there's nothing going on. But like if you look over here, there's no horizontal edge, so it doesn't detect it. It does detect this one that's diagonal because it's vertical, semi-vertical, but it doesn't detect the horizontal one, so we still need to do some more work. But just look at the horizontal edges, and there's your field. So now the tree vertical edge is not detected, but the horizontal one is detected, which is kind of cool. So we can have horizontal edges and vertical edges, and depending on what you care about, maybe you might only use one or the other. But generally people want both. So this is the entire image with all the edges. So now, all we need to do is just avoid the edges, right? Sounds simple. There's a lot of edges. So what are you going to do? So, and we can do the same thing for all 3 channels. Right now, that was all in like grayscale space, and so here's that one. And it's a little bit more clear. So there's like some of the people in the edge of the field are actually now highlighted because they were in some colors that we didn't detect them earlier. But that's sort of like just an added bonus that you can do. So how do we avoid them? So first we're going to start with a very simple toy problem. And you can imagine that the edges are symbolized by like the high values, and you want to find a path from the top to bottom of this matrix without hitting the high of numbers. So if you just like glance with your eyes, you kind of can see that maybe you can go from like the 0 to the 6 to the 0, and then you can go back to the 3 and then go back to the 0, and that'll give you a total of 9. And if you went the other way, and you kind of just went down from 0 to 0, that would get you, it sounds good, but then like you hit a 9 and there's no way out. So you kind of have to go down through the 9s, and then you get to 10, because you get 0, 0, 9, 1, and then 0. So you're better off taking the path to the left. Or I should say you're right. So basically, you're going to go down the path to the edge of the matrix. So like the question is, how do you find this path? Because this path looks like you kind of have to try everything. And so here we can use a little bit of dynamic programming. So this is kind of like a favorite topic of mine, which is you have optimal substructure, which means like you're going to be able to find some, you're going to be able to reuse parts of your problem, and then they're overlapping, so you can actually go and use memoization to like kind of save the results. So here's a way that you might set up this recursively. You might say, okay, we're at a particular row and column, and let's say we're at the end. So if the row is greater than the last row, we've fallen off the image, or we're at the column if we're at the row is the greater than the last row, then we're done. We've gone to the bottom of the image. Or if we're at the column, we've moved off to the side, then we've fallen off, and so we're just going to return infinity. Otherwise, we're just going to try to do this again, but try the cell to the path to the bottom, path below us, and path to the left, to the right of us. So basically kind of just go down, try each path below, and then kind of keep going. And we're going to just try this like forever. That's kind of the way to state the problem, but it sounds rather complicated. And we can simplify this a bunch. So here's the bottom-up approach. Just take the minimum of the current row. Take the top row, find the minimum value. Grab that minimum. Then take the next row, shift it 1 to the right and 1 to the left. So you can see this is sort of like xprev is going to be our friend everywhere here. So you take the 1 to the right, 1 to the left, then go down 1, so add them up. And then what that'll do is that'll be the best that you could have gone to the next row. And then just keep doing this until you get to the bottom, and that's the best you could have done. So you can see here in the first row, the best you could do is 0 in the middle. Then you can get to 0 on the second row, but you have to already pay 6 to get to the second row. And then the next one down, you get to 6, but the next one over there is already costs you 9. So the best you could do on the third row is 6. So that's how you know that you're going to end up having to go to the right. And then you can get to the bottom. You see it costs you 9, and then the bottom last row is 9. So that's the best you can do for the whole matrix. So and that's what that looks like. Just y plus the minimum of infinity and the shifted next row. That's all you have to do. So that gives us that matrix, and then we have to find our way back. So okay, you've kind of gotten to the bottom row and you see that it costs you 9, but you need to know what path you took to get there. And so the traditional way of doing this is like storing a lot of information about like what paths you took, but we can actually do something very simple. We can just go and say, we're going to trace back. So we can just trace back from the bottom and just say, pick the best element that there is on the bottom, because that's the best we can do. And then look there and just take the one that's smallest there, and go up to 9, then the best from there is 6, then go back up to 9, then the best there is 6, so we go up to 6, and then go back to 0, and that gives you the last. So that gives you the path, because all you do is you just follow the minimum back up. And so that's what that looks like. You basically reverse yourself, and you go back up, you travel back up, and then that returns the path that you took. So you first were on the third, then you were on the fourth, then you're on the fourth, and then you go back to 3 and 2. So that's sort of path. So that's kind of, that's all there is to it. But okay, let's see how this works in practice. So first of all, you need some IMIN, which is like gives you the argument of the kind of where was the minimum element. You need the shape, you need the convolution, you have the kernel, which kind of gives you the filter that gives you the edges, and then you can apply different versions of the Sobel filter to your matrix. One with doing it in red green blue space, or you could just do it on the level, and then you can find the minimum seam, and then you can remove a seam. And removing a seam is just removing that path. That's like the smallest path. So here's the original image, and here's it 1/3 smaller. So kind of can see, that's kind of cool. Like if you go back up, there's a bunch of field that's like kind of empty space in the picture, and when you remove 1/3 of the image, it doesn't look like a lot's changed, just the two farmers are much closer together. The farmer all the way on the left doesn't have any field next to him, so that part all got disappeared. So that's pretty neat. Can we do better? Well, we can create an interactive widget and let someone else reshape it in sort of at a time. So here's that. So here's it with 0 pixels removed. And here's it as we shrink it. So we can watch it in real time get smaller. It's kind of cool. And you can kind of see, I mean, eventually this thing has to delete people because there's not room to not delete people. But in the beginning, it kind of looks normal, and then eventually there's just not much left of the image. So that's pretty cool. And the code to do that is very easy. You can just do a notebook with this like interaction. So now you have PyKX. All you need to do is just you wrap your function that's going to do the image removal from Q, and you just say it's an interactive element, and then you have this interaction. That's it. Yeah.